Thank you for taking the time today to join us. On behalf of my colleagues, Beth Blakney, Jayson Lee, Sean O'Neill, and Marilyn Ross, I'll be presenting our efforts at preserving the space domain here at MITRE. Space is without structures or rules, and in the absence of coordinated control, the basic premise of space traffic management is due regard. That is, each operator is accountable for their own safety and the safety of others. The real danger to the space domain comes because of that lack of structure, which translates into a lack of risk management for the space environment itself. Each operator is making their own decisions, and that could become the wild, wild west. The answer is providing just enough structure to make the individual self-interest of the operator who's trying to manage their operation safely synonymous with preserving the space domain. We think of collaborative decision-making, where operators still make their own individual decisions, but they're aware across the entire operation of what others are doing, and those actions are coordinated with a shared picture. The structure starts in planning, where users share decisions and support tools to understand the constraints of their operation. Preserving the space domain is about ensuring the regions of space don't experience cascading debris events, and that the spectrum is not so crowded as to degrade the performance of planned communications. That relies on the insights the operators can receive when making their decisions, insights they gain from coordination with others. It also requires the coordination of space resources to be fair and impartial enough to avoid contention. The link is a set of positive behaviors that tie the individual risk management to the effects that it has on others. So how does space traffic management provide that minimum structure to connect the operator's decisions to the management of the space domain risks? It begins in the planning and analytical views to understand the risks a new operation poses to those already in operations and to other planned operations that are still in development. It expands into operational views that look at the interactions between operators as they make routine decisions to maneuver or change their operation. And it has applications that add value from space traffic coordinators to help with the assurance of the mission and connecting those actions to the health of the space domain itself. What type of decisions do we envision at each level? Well, for planning, which happens long in advance and involves equity issues between multiple parties, the coordination has to be centralized because of those equity issues. For operations, it's more on the hours and days schedule, where pairwise operators can understand their interactions and negotiate a settlement. Finally, in runtime decisions, the time is so short that the operators can't provide useful human input. The speed of the decisions is between computers, machine to machine. The equity decisions that are made in planning need global arbitration. Planning of orbits and spectrum allocation will involve multi-party deliberations based on the knowledge of the existing and planned satellites and the existing and planned spectrum use. And they'll have to operate according to some norms about how those equity decisions are made. The operational decisions are working out the actions of two parties that are going to have some level of interaction with each other for whatever reason. For maneuvers, space traffic managements or space traffic coordinators can provide knowledge on the objects of concern. If there's a decision to be made about debris remediation, this can be part of the information shared by those organizations concerning lethal debris or the risks from large debris objects that might break up. Repair and decommissioning decisions can be made based on the knowledge of how difficult it will be to deorbit, move to the graveyard, or get a proximity or a rendezvous operation in place to repair the vehicle. Runtime decisions, as we've said before, are machine to machine. They could be about collision avoidance. Some have suggested decisions to manage spectrum in close proximity to others. And of course, proximity and rendezvous operations also require tight coordination. Looking at those decisions, we worked with internal subject matter experts and individuals from industry to come up with a set of risks that affect the operator's mission assurance and the space domain health. By looking at the risks and prioritizing them, we concluded with industry that awareness and information, governance and debris, blocks, space were the three biggest categories, and focused on those areas. We began to build line of sight risk models that connect these risks with the behaviors or outcomes that we hope to achieve as a community to preserve the space domain. This example shows how the presence of lethal debris and the increase of missions will combine to increase the importance of shared awareness. That awareness is critical to planning orbits, deciding on debris remediation, and deciding the importance of onboard avoidance algorithms. In the trace, we see how the risks of inaccurate or incomplete information could negate that shared awareness. So we add norms for equitable coordination to address those gaps. And finally, the risk of mass debris generation from a collision or inconsistent enforcement actions must be countered by tight operational decision-making and possibly even runtime onboard collision avoidance, so that when an encounter without coordination is made, the system remains safe. When we started the workshops, we thought the focus would be on the actual collaboration. So we built an emulator that could be used in planning and operational decision-making to visualize the collaboration and value of information. But as we did the deeper dive into the risks and started to identify the variety of risks that exist, we shifted our focus. The models for coordination could come back into play as we move into the solution space and begin to evaluate them. Another model would be necessary to evaluate runtime collaboration. So in conclusion, we've developed with industry a set of risks affecting mission assurance, which could also impact the safety and health of the space domain. And we've mapped those risks to behaviors and outcomes and the decisions that will be necessary to mitigate the risks. By linking these decisions and information into the operations of individual operators, we hope to incentivize the behaviors that would preserve the space domain. The next steps are to refine those models and translate those behaviors into policies and norms that would assure space's preservation. Thank you for your attention and your participation today.